You're back again for another astronomy video. Now, I know that we've had some problems with it posting through Canvas. Again, if I'm using this in the spring, ignore that. But since you're in this fall, since this is the first time I'm making it, I'm going to figure out what's going on. They did some maintenance today. I'm hoping that that fixes our issues in the future. If not, please keep letting me know. Send me messages, send me emails. I promise I will fix it as soon as I can, or I'll at least give you a workaround as soon as I can. But aside from that, things outside of our control, back to the notes. So I kept telling you that not everything's maybe exactly the way that I was telling you. And here's one reason why, and here's one of the big reasons why. When I introduced to you what revolution was, I said it's Earth's path around a fixed point in space. Well, the sun is basically fixed, but it's not, because it's actually not stationary. The sun is moving along with us. Now, why do you think that the sun is moving along with us? We'll talk about it in class, but see if you can figure out some ideas. We do know this, we can measure this, we can use the math to figure this out. But, you can see on your notes, it says that it's because of the solar system's barycenter, but think about why it's not the same all the time. So, what does that really mean for us, and what else moves, and what does that mean for us? Well, moon. The moon moves. We know that. We see the moon as it goes around during the month. We see the different phases of the moon. And I had you make that sheet with the phases of the moon on it. And now we're actually going to explain what they are and why it's important. We only have one natural satellite. It's the moon. It has a name. Maybe some of you know the name. Tell me if you know the name in class when you see me again. But we also know that the moon orbits the Earth. It revolves around the Earth in a period of 29 days. Now that's going to be significant because as the moon spins, as it rotates, it's going to go around, it's going to revolve. We have a special name for that, and we're going to talk about it here in a little bit. You don't need to know how far away the moon is. I know I listed it. You don't need to know that because it's in miles and everything we do is in kilometers. That's just for reference. It's pretty far away. Now, I know that you probably are thinking, why do I care? It's the moon. Great. It's in the sky. I see it. Sometimes it's out during the day. Who cares? Well, I also, just for reference here, put a GIF, whatever. Again, don't fight me on that. I don't care. Of how quickly it takes light to go from the Earth to the moon. Now, to get from the sun, it takes light about 8 minutes. So if the sun were to magically go out and the sun were to stop shining, we wouldn't know for 8 whole minutes. But the sun is about 150 million kilometers away, or since we're in America, about 93 million miles away. That's a really, really quick speed that the speed of light has to be in order to get 93 million miles in 8 minutes. But again, let's get off that. That's me going into my physics world, and some of you like that, and most of you are going to roll your eyes. Whatever. Phases of the moon. Why are they important? Well, we have two different types. We have a waning moon or a waxing moon. When you see the moon is waning, it means it's getting smaller. It means we're seeing less of it in the sky. When it's a waxing moon, that means it's getting larger. It means we're seeing more of it in the sky. But we tack a second word onto that. It's not just a waning moon or a waxing moon. We can either have it be a crescent moon, or it can be a gibbous moon. And a crescent means we see about a quarter to a third of it. It's come somewhere in that kind of, general frame. And a gibbous means we see about 3/4 of it. So if it's growing and you can see 3/4 of it, it's a waxing gibbous. If it's getting smaller and you can only see a bit of it, then it's a waning crescent. You put all these different terms and all these different combinations in addition to the first quarter, third quarter, new, and full, and then you get your phases of the moon. It's pretty simple. The next slide should look pretty obvious to you. You already used it in class. But also, let's think about why I didn't explain the other 4 yet. Part of it is because of that whole spinning, rotating thing that I was telling you about. It happens to be that the moon and the Earth are something called tidally locked. And the time it takes the moon to revolve is the same time it takes it to rotate. 29 days, which means that the reason we see different parts of the moon is not because it's getting blocked, it's not because it's reflections and all that, it's as we're seeing it as a different point in its path is why it looks different in the sky. We also know that the moon is about a sixth of the size of Earth, which means it has about a sixth of the gravity if you were going to go and jump on it or knock golf balls off of it like Apollo 14 did. But that also means that the moon affects our tides. And if you like to go swimming in the ocean, or you like to go deep sea fishing or anything like that, or maybe not deep sea, but shore fishing off a pier, if you've ever been down to the coast and done that, the tides are being affected by the moon. But it's not exactly what you think. We're still kind of working out, when I say we're, I mean scientists in general, are still kind of working out what exactly happens with the tides and why they do what they do. But we think, and we're pretty confident, that it's not like it's just the water getting pulled or getting contracted by the moon's gravitational pull. It's actually deforming the Earth underneath the oceans. It's actually kind of squeezing and compressing the ground underneath it, which pushes the water out or pulls it in depending on where you're at. This leads to the first of the 2 times in the semester we're going to talk about tides. Now, we have a bunch of different names for it, and we're going to get into some now, and we're going to get into some later when we talk about coastal processes and the ocean and shorelines and things like that, stuff you've already talked about. And for you that asked me, I'm not going to say your name, why do we keep learning the water cycle? This is going to be part of that too. Sorry. But why? What does it mean? I'm definitely hinting, nudging this next slide. Spring tides and neap tides. Not that difficult once you get the hang of it. Now, a spring tide is going to be a full or a new moon. So go back to that sheet that I told you was going to be a reference sheet. New moon, full moon. We see none of the moon. We see all of the moon. Why is a spring tide with this? Well, the sun and the moon and the earth are all going to be in a line, which means those gravitational forces are going to be the strongest. It's going to be the largest difference between high and low tides. The other one is a neap tide, and that's going to have a smaller difference between high and low tides. And why is that? Well, you have the sun over here and you have the moon here, but the earth is down here out of line. Those gravitational forces aren't lining up. They're not as strong. They're not all working together. Therefore, it's not producing as much of a pull on the earth. It's not changing and deforming the ground underneath it. It's not going to have as large of an effect on the tides. We're almost done. Promise. Before we end today, and we're going to end with something that we're going to talk about in our next unit, energy sources, I need you to keep these 2 things separate. Now, I told you we're going to talk about them again, so you should remember it, if nothing else, for this test, because it's getting ready to pop up again next week. I need you to keep the terms nuclear fission and nuclear fusion separated. They are not the same thing. They're kind of opposites of each other. When fission occurs, this is what we can do on Earth. We can produce fission in nuclear power plants. That's how nuclear power happens. And it's like when atoms are split apart, they fizz apart like you shook a soda up and then it kind of, fizzes out the top, it spews out the top. That's kind of what fission is. You're splitting these atoms apart. Energy is released because we're making them into smaller little subsections. This is easier to do, and it's what we can reproduce on Earth. It's what we can do reliably on Earth. That's why nuclear power can work, because we can reliably and safely do this. The opposite of that is fusion, and that's when you take 2 hydrogen or 4 hydrogen or whatever hydrogen atoms and you smash them together. Now, this doesn't seem like it'd be that difficult, but it takes an absolutely insane amount of energy to get these 2 positive things to go together. Think of a magnet. Positive, negative, not a problem. Positive, positive. Every time you push that magnet together, it wants to fight. Well, that's what you're doing on this atomic scale. You're pushing 2 positive ends of a magnet together and trying to make them be happy with each other. It takes a lot of energy, but when it actually occurs, when fusion is actually able to occur, you have a just off the charts amount of energy that is produced from this. Fusion is what happens inside of stars and is what happens inside of our sun. And without fusion, the sun is not going to have the energy that it has right now, and it's not going to be able to give us that light and the heat, and it's not going to be able to sustain life on Earth as we know it. Now, I know that I'd also, on the slides and maybe in class, if you ask me, we can talk about it a little bit, talk about fusion and nuclear weapons and atomic bombs and stuff like that. Promise we'll get to that if that's what you're into, if that's what you're excited about. We're going to talk about that in energy sources. We're not going to talk about it quite yet, but I promise that we're going to get to it. Last thing, why can we not produce fusion on Earth? We'll talk about it again in energy sources, but if you look at those numbers, look at the temperature and the pressure needed to create fusion. For reference, you know what temperature is. When you go outside, there's 1 atmosphere of pressure. 1. Go look at the number on the slide and figure out how many atmospheres are needed in order to produce and have fusion occur. Hopefully, this is notes video 3. You got something out of it. It's helping you get through the notes. We're almost done with astronomy notes, which means we're almost done with the unit, which means you should probably start studying because a test might be coming up pretty soon. If you have any questions, please send me an email. Please send me a Canvas message. Talk to me in class. Whatever you need to do, I am willing to help. We're kind of all in this boat together. I don't know what it's going to look like, but I promise we'll talk about the test. It's still at least a week away, but start studying now. I'll give you all the details about it. I'll tell you what it looks like. We'll go over it. We'll do a review. I'm not going to leave you hanging, but you got to study and you got to do your part. You can do that. I know you can. Talk to you soon. Bye.